All right, so I got a real simple one for you here. We're going to do the pivot formula for calculating determinants. So here you get an A that's a lower triangular matrix times an upper triangular matrix, right? If there's no row swaps required, this is just real straightforward. The lower triangular matrix, remember, is the inverse of the product of all the elimination matrices. So that thing there looks something like this, right? It's got a big old fat zero up here. It's got a mess of ones down the diagonal, and it's got some nonsense down here, right? There's some entries down there, but this matrix is going to have ones down the diagonal. Now the U matrix here, that guy's going to be upper triangular, so it's going to have a big fat zero down here. It might have some entries up here in the top corner, and then it's going to have some numbers down here. These numbers are all the pivots. So we're going to have pivot 1, pivot 2, all the way down out to pivot, I don't know, pivot n or whatever we get. In the case that I've got a matrix that I can decompose like this with, again, no row exchanges, the determinant of A, right? So determinant of A, which we sometimes write as like an absolute value of the matrix A, that determinant is just going to be P1 times P2 times just all the way out to Pn, right? So we're just going to multiply down the diagonal of that U matrix. This is actually how the computer does it for reference. So if you ask a computer the determinant of a matrix, what it's going to do is it's going to get it into lower triangular, upper triangular mode, and it's going to multiply the pivots. It doesn't even actually need to figure out what the L matrix is. Remember, because we're going to have some, like after we do elimination, we'll have something like L inverse A is U. And then the pivots are just down the diagonal of U. I don't even actually need to know what the matrix L is, so I don't have to calculate the inverse of L. I can just go ahead and grab the pivots off of U. So that's kind of our easiest option. A quick example of this is if we've got our matrix A, B, C, D, right? And now I'm thinking, all right, I'm going to do a little bit of a row operation here, right? And the row operation I'm going to do is the new row 2 is the old row 2 minus C over A row 1. Right, so I'm just going to write C over A row 1. So if I take this guy here, I'm multiplying by minus C over A. So I'm going to get minus C here. I'm going to get minus BC over A there. I'm going to do this addition. I'm going to get to my new matrix, right, after my elimination step. And that new matrix is going to be A, B, 0, and D minus BC over A there. And then I'm going to take this product down the pivots, right? So the pivots are A and D minus BC over A. So the determinant, actually, let's use our other symbol. So our other symbol is going to be with absolute value bars. So determinant of A, B, C, D is going to be the product of these two pivots. So that's going to be A times D minus BC over A, which we can simplify to A, oops, not B. Come on, go away. AD minus BC. That's our 2x2 determinant formula that we know and love, right? Hey, cool, it still works, right? It's the product of the pivots. Awesome. This is mostly mentioned here so that you know how the computer calculates pivots. Or calculates determinants. I just don't want that to be a mystery. Because the other formulas I'm going to show you are really awful. And the computer doesn't do the awful way. The computer just does this. The one caveat that I'm going to add here is if you have to do row exchanges, right? Every row exchange you do is going to add a minus sign. So if you have to do 2 row exchanges, you're going to get back to the product of the pivots. If you have to do a single row exchange, you'll get negative the product of the pivots. If you have to do 3 row exchanges, you'll get negative, 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 which is just 1 negative times the product of the pivots. So that's all I need from this one. Thanks, guys.